Hi everyone. Let's wait for 5 more minutes until 8:05.
Hi, Chow, how are you?
Cool, how are you?
Good, good. Sorry, I wasn't in the last lecture. Uh, have you made any updates regarding exam pattern? Whether it will
Uh,
be
no,
no.
no, we haven't received the final confirmation from the university. So it may be known in next week or weeks at the beginning of week 6.
Okay, all right,
Yeah.
thanks.
Just a quick question, doctor, is regarding to assessment one. Any idea when we will get the results?
It will take 2 weeks to finish the marking, so it will be released after next Wednesday. So I will make an announcement when the market is available.
Okay, thank you.
Thank you.
Okay, I think we can start. So from this week's on, we will be learning more modern deep learning and neural network structures. So this week we're going to learn the basics that will be used in all the modern and advanced neural networks data structures. And in next week, we're going to learn structures working specifically for computer vision. And in the week 6, we'll be learning some neural network structures that is tailored for time series data and for NLP kind of tasks. And we have learned some conventional models in the first half of these subjects. like linear regression and SVM for classification. And we also learn this very widely used task like classification, clustering, regressions. And we are going to um, learn how to deal with this task using the modern structures, the deep learning and neural networks. So this week is about the basics. So we'll learn some basic computation underlying these neural network structures and some basic building blocks that will be used to build up the complicated networks. So let's first look at the task we're going to deal with. So previously, we mainly work on the single class classification or binary classification task. So just like spam email detection, so we classify the email as either spam or not spam. What if we make the task more complicated? Like if what if there are more than two output candidate classes? Let's say for this handwritten digit recognition task, we will have 10 possible output, like from 0 to 9. So given an input image containing single handwritten digit, we would expect the model to predict what digit is the image of. So is it handwritten 0 or handwritten 5, 6, 7? So we need the model to predict the class of the input image. So this is multi-class classifications. And to deal with this task, we also need some techniques that we need to get familiar with. So first one is one-hot encoding. So unlike the binary classifications, which we only predict one score for the prediction, like the likelihood of the input is belonging to a certain category, so we only need one score or one probability to indicate such preference or belongingness. But for multi-class classification task, a single probability or single score is not enough anymore. So, but for the input, we may only receive just one value indicating which class this sample belongs to. So we need to convert this single value into some format that is convenient for the multi-class classification model to compare with. So we need to use one-hot encodings. So we need to convert this single value into a vector of class probability. So for the true label, we thereby would have binary vectors. So this is a vector holding only binary values, either 0 and 1. And the value 1 would indicate that the input sample would belongs to specific class. So for this handwritten digit recognition task, there are 10 possible classes. So we need a vector of 10 values to represent the belongingness to each class, because the input can only belong to one class, and there should be only one values in these binary vectors, and the total number of entries in this vector is 10, corresponding to the total number of classes. So we need this one-hot encoding method to prepare the labels for multi-class classification task, so that at the when the model make a prediction, it will predict, let's say, this would be the prediction from the model. The model will predict a vector of probability that the input belongs to each class. So it may predict that for the first category, there's like maybe 10% probability belongs to the first class, maybe 5% belong to in second class, maybe 1% for the third class. This is no 1%. And so on. And then finally, it may make decisions like 0.85, maybe 85% belong to in the last class. So the model for multi-class classification will generate a probability vector indicating the indicating the probability of the input image belongs to each class. And then we are going to compare this label vector and the probability vector generated from the model to see if the prediction is matching with the true label. Because in this case, the true label says it should be digit 3 because this is digit 0, digit 1, 2, 3, and so on. This should be digit 9. And the prediction says the highest possibility belongs to digit 9. So this one doesn't matching. So so during the training phases, we are going to tune the parameters, the model parameters, so that the model can predict probability vector with the for this one for the value at this place corresponding to this digit 3 probability to be the highest probability value. So that is the purpose of one-hot encoding. So we need to prepare the label vector so that it can be compared with the model prediction. And we will also construct our loss function based on such comparison. And then we need to introduce the softmax function. So the model prediction, the prediction of the model, normally, let's say, for example, for the regression model, the predicted output is continuous value. So, but for multi-class classification task, it's kind of similar, but the difference is the number of the output, but it will not predict the probability directly. It will generate some output, like the score, like the preference or likelihood that indicating how likely the input image will belong to each class. So for example, this may be the output from the model. So it will generate a vector of scores called logits. So these logits are just some raw and unnormalized output scores. So there is no limit on the range of these values. So it can be very high, like maybe 99, and some category has score like 0.3, 0.4. The range of these scores can vary a lot, and the model can even predict some negative values for certain categories. So there is no limitation on the score predicted by the model. So we need a way to normalize these values uh, into the probability kind of format. So it will ease the interpretation of the model prediction result, right? So it's hard to interpret some kind of score with a variable range, and it is easier for us to interpret the probability values. And the probability values should have some properties, like all the values should be strictly positive values, and the range of this probability must be within 0 and 1. And the sum of all these probabilities should equals to 1 because it covers all the possibilities. And if we sum all the probability values it from all the possible classes, so their sum must be equal to 1 exactly. So we need a way to change this prediction score into some probabilities. And actually, we are converting a vector of such scores, so called logits, to a vector of probabilities. Just like I mentioned in previous slides, the output of model prediction is expected to be a vector of probabilities belonging to each class. So we need a way to convert a vector of scores to a vector of probabilities for each corresponding to each class. And then we need to use the softmax function to do such conversion. So we can see that the input of softmax function is phi, and it is a real number vector containing k entries, and this k is corresponding to the k classes or k candidate output. And the output of softmax function is the probability vector. And this is a vector, it is also a vector of k entries corresponding to the number of entries in the input vectors. And this is the equation. So it is calculating the exponential of each entries in the logits, and then divided by the sum of this and exponential of scores, exponential of the scores. So the result will guarantee that all the converted value must be within the range 0 and 1, and their sum is exactly 1. And thereby, we can treat this converted value as probabilities. So after softmax function, we will get a probability vector. Is there any questions till now? This is important for classification task and multi-class classification task. So yeah, all good till now? Great.
Sorry, can I just ask, with softmax, what does it is it under, how do you incorporate it in code? Is it under another platform or
Um,
so usually like
Usually, if you are using some framework like TensorFlow or PyTorch, it is built into the model data structure or the loss function you specified. So you don't
yeah,
need to worry about that, but you need to know that it is using such kind of
okay,
softmax function
yep, yep,
because later on after we know that we are using softmax function to convert the logits to a vector of probability, we
Yes.
understand what cross entropy is doing. So cross entropy will be widely used in the loss function. So you know how the loss function are built for uh, with this
Yep.
techniques.
Okay, thank you.
Okay. Okay, great. So we know that we can now convert the vector of scores into a vector of probabilities. And now it's time to compare the vector of probabilities with this binary vector indicating the true label of the input, right? So we need to use the cross entropy. So the cross entropy, uh, it is a concept from information theory, and it is widely used in machine learning. It is particularly used in the loss function for classification task. So the purpose of this cross entropy is to measure the dissimilarity between y and p. So y would be the true label vector, the binary vector, and p would be the probability vector generated from the um, model output and converted using the softmax. So this is the vector p representing the probability vector. So it is measuring the dissimilarity between y and p, and because it is measuring the dissimilarity, intuitively we know that the lower the value, the two probability vector. So we would expect this cross entropy measure to be as low as possible. So it align with our expectation for loss function, right? We want to minimize the loss function so that the model can be proved to be optimal. And then we would expect the cross entropy to be as small as possible so that the predicted probability vector would be as similar as possible to the true label vector. And the input true label vector and the probability vector from the model are all k-dimension vectors, k corresponding to the k possible classes, and they are all non-negative entries. So it is probability vectors, so it must be in the range between 0 and 1, right? And for true vector, the value can only be either 0 or 1. So they are all non-negative entries, and their sum of their entries values must be exactly 1 so that we can interpret each entry as a probability. And this is the equation of cross entropy. So it is calculated as the entry of label vector multiply the log of the probability, predicted probability for each class. And then we do the sum of all these terms for each pair of the entries in these two vectors. And we take the negative, and this will be the cross entropy. And you must be careful, don't swap these two variables. The true label vector must come first, and the predicted probability must come as the second parameter. And so correspondingly, let's say we need to calculate the log of the predicted probability and multiply the true label values. So that will make this equation very easy, right? We know that the y can only take values either 0 or 1, and there can only be 1 in all the entries. So after multiplications, we know that there must be only one term that is corresponding to the true class were left, because all the other terms will be 0, because whatever log value of the probability times 0 value of y will be 0. So only when YL corresponding to the true class will be 1, in that case, the log probability will be left. So let's take a example. Let's say y equals to 0, 1, 0, and p equals to maybe 0 0.1, 0 0.7, 0 0.2. So if we expand the equation, so we will get, so y1 multiply the log of p1, so that would be 0 multiply log 0 0.1 plus 1 multiply log 0 0.7 plus 0 multiply log 0 0.2. We can observe that these two terms must be 0, right? Because 0 multiply any value will be 0. So only this term will be left. Only the probability of true class will be left. So that will make this cross entropy calculation of cross entropy be very, very easy. We only calculate this the multiplication corresponding to the true class label, and then take its negative. So we can we can just simply say the cross entropy is just it's just a selection of the log probability of the true class. So that would be one just short intuitive understanding for this equation. And this score, again, this score would be representing the dissimilarity between the label vector and the probability vector. And we use this cross entropy as our loss function of the model, multi-class classification model. And we can also, of course, use the squared L2 norm or the L1 norm to replace the cross entropy. But cross entropy is always the better choice or preferred. So although the L1 and L2 norm can find the similar optimal point, but it is less stable than the cross entropy. And so cross entropy is a better choice. So in combination with the softmax function, so the cross entropy can make the gradient of the loss function in a very simple form, and it will help the optimization process to be smooth and much quicker than the L2 and L1 norm. And it is the cross entropy is um, from the information theory and also based on the maximum likelihood techniques. So it is more mathematical founding than the other two. And the L1, L2 norm is still applicable, but they are maybe slower and less stable during the training process. And they are more naturally suitable for regression tasks instead of the classification task. So cross entropy is the better choice, but we can also use this tool in using the L2 and L1 norm as the loss function. Okay, is it all right for this cross
Sir,
entropy?
one question, sir. Sir, here, what is the log scale? Is it E or 10?
It should be E. It should be log. So in machine learning context, normally there you it is also called sometimes it's read log as log. So just mathematically they are not equivalent, but in the optimization context, they will optimize the model towards the same optimal point. So
Hmm.
so just the notation different, but underlying they are referring to like log.
Okay. So can we refer it to as y1 e to the power of p1? y1 into e to the power of p1?
Log is the reverse of exponential log. So let's say y is equal to x, then x that's the equation, right?
Okay.
So this is not equivalent to exponential of PL. It is not equal.
Okay.
I just used the calculator or the web and search the log 0.7 is minus 0.5 blah blah blah. But the log 0.7 is minus 0.3566.
Yes, I mean
They are
log
not
no,
equal.
normally mathematically log means uh log with 10 as the base and log that is log e as the base. So mathematically it is like this, but in the machine learning or deep learning context, just maybe because the people are lazy, they don't explicitly write uh, log log e as log. They just ignore this e because most of the time it is calculating the exponential of something and using the log of something in the equation will be make calculating the gradient more convenient. And yeah, so most of the time it is referring to log e.
Thank
If
you.
you read log something in the equation, it will mean log e, log something.
Okay, thank you so much. That was really good.
Okay, anything else? All good? Okay, let's move on. So now let's look at our example again, the handwritten digit recognition task. So let's define our context. So we have input, and input are some vectors. If we have total n data samples, we will have n feature vectors, and each feature vector will have d elements corresponding to the d features. In this digit recognition task, if the image come in size 16 by 16, this is the dimension of the image. So it is the square image, and it has 16 pixels on the row and 16 pixels on the column. We would then have d equals to 256. So that would be the number of features, because in this task, we're going to treat each pixel as an independent feature. So because we have 16 by 16 pixels in each input image, if we flex them into a column vector, we will get a vector of 256 entries, and each entry is corresponding to 1 pixel value in the image. So here in this case, if the image comes in size 16 by 16, we will get d equals to 256. But each image is treated as one vector. And we will have some labels, and these labels are converted using one-hot encoding. So they are already converted into the vector form. So it is now each y now is a binary vector of k entries, and the k is corresponding to the class numbers. And if given this process has been given in this remark. So if we are given labels that are scalar values from 0 to 9, we need to use one-hot encoding to convert it to this format. We need to convert it to this binary vector. Okay, that's context for the input and output from the input information for the model. So let's see how can we what model can we use to generate the prediction result by if we are feeding such input into the model. So we are going to use the softmax classifier. So the basic idea of softmax classifier is we first use this model to generate a vector of scores, just like this. We first generate a vector of logit, and then we convert this logit into the probability. And the category or the class that is holding the highest probability will indicate the belongingness of this input data sample. So how can we get those logits or the category scores? So we are using this form. So it is familiar. You may be familiar with this one. It is similar to the linear regression task. So basically, it is multiplying a weight matrix and the feature vector. So it will be a linear combination between the weight matrix and the feature vector, and the result would be the class scores or the category scores. So if we check the shape of the of W and X, we can see that the matrix X has k rows corresponding the class numbers. K is class numbers, and D, that is the feature numbers. And X is the feature vector, that is column vector. It has D entries. So the result of this matrix and vector multiplication would be a vector of k of k entries, or say k rows and one column. So that would also be a column vector of k entries. So each entry in this phi vector will be corresponding to the class score for each class, right? So we have 10 entries, and each entry is corresponding to one class out of this total k classes. So with this model defined, our task now is going to tune these values, right? Tune the value in this matrix X so that after this multiplication, this phi vector would holding some expected score. So ideally, the true class should holding the highest score. But now this phi has not been converted to the probability vector yet. So after the conversion, the highest score will be corresponding to the highest probability. So this matrix W is holding all the parameters, parameters to tune during the training phases. So this is an example of example output of this phi vector. So we can see that, as we said before, there's no limitation on the value range in this score. So it can have like high score as 15 and low score as even -8. So it can even produce some negative scores for certain classes. So we need some way to normalize this result to make it more interpretable. And we also want to use to convert it to some way that can facilitate our optimization process. So we want the model training to, let's say, ideally, if we are going to tune the model manually, we may following some order saying, I want to tune the parameter so that the model can, we want to guarantee that the correct class can be predicted correctly first, and then we think about how to surprise the probability of other wrong class candidates scores. So we may follow in such kind of order if we tune it manually, and the softmax function can help us to do that. So after the conversion, we can see that it amplifies the probability of the correct category and suppress the signal of the wrong class categories. So just for your information, this kind of skewness for the probability distribution will help the optimization to converge and reach the optimal situations more quicker and stable. So it is doing such skewing on purpose, this is not a mismatching between these two distribution. So as we said, we need to apply the softmax function to convert this to convert this logis vector into a probability vector. So after the conversion, we will get a vector of k values, and each value would corresponding to the probability of the input belonging to a certain class, and their total would be equal to 1. And now P is the probability vector. Now it's time to compare this probability vector predicted by the model with the true binary label vector, right? So we use the cross entropy loss. We are calculating or measuring the dissimilarity between the probability distribution and the true label binary distribution. And the lower the value, the better. So this will be our loss function. So we want to minimize this cross entropy loss. This is the workflow illustration for the whole process. So given an input feature vector x, we multiply it with a weight matrix, and we will get a vector of scores or logits. And we apply the softmax function to convert it into a probability vector. And now it's time to compare the probability vector with the label vector. And we can calculate the cross entropy and to build our loss function. And this value would be measuring how far the model prediction is from the true label we are expecting. Is there any question till now?
Doctor, for these equations for exams, how do we prepare? What do we have to know for?
You don't which equations are you referring to? I think there are only two equations here. You don't need to memorize that as long as you can express it using your own language. Let's say, what's the purpose of the cross entropy? What is its measuring? And what does softmatrix function do? Something like that. You don't need to memorize those equations, but you need to understand their purpose, what it is doing, and using your own language.
So what I mean is, in exam, will there be given some values, use these equations and find out the result? Will that be something like that?
It's not a mathematics or calculation course, so it won't give you say you have two vectors of certain values, like follow what's the cross entropy loss of these two vectors. There won't be such kind of questions in the final exam.
Thank you.
Okay. But you need to understand the concept, right? You need to understand the concept and get ready to explain them in your own language. Okay, that's the workflow of using softmax classifier to do the multi-class classification task. Here are some limitations of the softmax classifier. So if we have a feature, we have 1,000 features, and if we have 10 class to predict, the total number of parameters would be 10K, right? So we need to, according to the size of the weight matrix. So the total number of values that we need to tune in this matrix is equivalent to the total number of entries in this W matrix. And the total numbers will be K, that is the class numbers, multiply the feature numbers, right? Because the shape must be matching with the input vector and the output vector. So the shape of the weight matrix must be in this size. So class numbers multiply the feature numbers. If we go back, we can see this is the class numbers multiply the feature numbers. And we need to tune 10K parameters. So for even larger data set, like ImageNet, image recognition task. So this is like popular computer vision dataset. We need to classify the image into 1,000 categories. And in that case, we may need 1 million parameters. And let's say for even more general tasks, say for face recognition, we may have 1 million classes because each class is corresponding to each individual people or each identity. So we need that many classes. And then the parameter numbers will be increased to 1 giga. So that will be requiring a lot of computation and memory powers. So what if the classes numbers increase to 1 giga? And you can imagine how large the parameter number is. So that's the limitation of softmax classifier. So it will require a lot of parameters to tune.
Excuse me, Dr. Zhen.
Yeah.
Sorry for there might be silly questions. What's the difference between features and classes? I may have confused before.
Feature is the input and classes is the output. So in this example, let's say for this digit recognition task, so feature would be, so you know that for digit image, it is kind of, let's say, just this image patch, right? So in computer or in memory, it is represented using the matrix. So for background, it may all zeros, and it use for binary image, it is using 1 to represent pixel values. So this would how the zero image look like. Let me zero in between. So you understand, right? Is it okay for you?
Yeah.
Yeah. So this is the representation for a digital image. So each pixel is holding a pixel value. And let's say we have this is 16 by 16 image. So that means we have 16 pixels on the pixels on the columns, and 16 pixels on the rows, and or 16 rows and 16 columns, and we will have in total 256 pixels. And if we flat this matrix into a very long column vector, this will be a vector of 256 by 1. So inside this vector, it will have some value like this. So we just flat this matrix into a single column vector. And each entry here is corresponding to each pixel value, and we just treat this each entry as an independent feature. So this 256 will be the number of features, right?
Yes, got it.
And the label or the classes number is the output. So this feature vector is related to input, and this class numbers is related to the output. So how many values can we expect as the output? So for this recognition or classification task, we are expecting the output can only be, let's say, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Can only be these 10 values. It cannot predict class 10 because there's no such category as expected as the output. So the output can only have these 10 distinct values corresponding to 10 independent classes. Of course, we need to use one-hot encoding to convert it into the binary vector format. But you know that there are single values corresponding to the expected corresponding to the number of classes, or say the class index. There are 10 possible class index as the output.
Yeah, got it. Thank you so much. I'm with
Okay.
you.
Any other questions? Okay. I think we can have 5 minutes break. Then we will start to learn the deep learning structures to deal with this regression or classification task. Okay. Let's come back at 9:03, and then we continue.
Thank you. Hi, I've got a question, Doctor. It's
Yeah.
Kathy here. So softmax classifier doesn't scale well from my notes when the number of classes become very large. What's that? How large is that? Like, is that extremely like what, 20 or 1,000 classifications? Or would that be a part of what we're going to do in our assignment, finding out that? Or
Sorry, I didn't get the question.
so with the softmax classifier,
Yeah.
in my notes it says the softmax classifier does not scale well when the number of classes become very large.
Yes.
So the number of classifications. So even if it's used for a multi-class classification, what is the maximum would you use for that formula?
Um,
Like,
so this is a basic, you can treat this softmax classifier as some basic computation
yeah,
method. Uh, you will see later today that deep learning models are using some similar computation with this softmax classifier. So normally we don't do the classification using this softmax classifier. We will use the deep learning neural
oh,
networks
okay,
to do the
yeah,
task. So
okay,
here is just the core is to know this like this is the basic computation we need
yes,
to understand. So we multiply weight matrix with the input vector, and we can generate a vector of scores. And if we want to convert some vector scores into some probability vector, we need to use softmax function.
yeah,
And we, if we want to compare the probability vector with the binary label vector, we need to use the cross entropy. That's the key point.
yeah, yeah,
Yeah, we don't
okay,
use the softmax classifier to do the task. We will use
okay,
the neural networks.
all right, thank you.
Okay, let's continue.
Sorry, Dr. Zen.
Yeah.
I got a question. Can you go back to the previous slide? One more? Yeah, this one. Is it the vector size of X, is it different from phi? Was it? The blue one is psi?
It's different because the size of X is D. D is the feature numbers, and K is the class numbers. So they must be like different. Not must be like most of the time. If they are same, it is a coincidence.
Got it. Thank you.
Doctor, I have a question about this. Like, this might be a silly question. Maybe I missed something. With this lecture notes, and when I refer the module 4, I mean, is there anywhere else that I can see, I should look at or read any other notes or anything? So, for an example, the software function is not on this LMS module 4 where I am looking at.
Yeah,
Uh,
those LMS page is just for your information. You can treat it as the supplementary materials. So for the assessment of these subjects, like the assignment and final exam, you can simply following the lecture slides, the contents I covered during the lab sessions.
okay. Yeah. Is there rather than your lab sessions and lectures, are there any other lecture notes explaining these slides?
Not really.
Okay.
So if you cannot find the contents on those pages, so um, then then no.
No. Mhm. So
Okay.
this, for me, like, it looks like this, lecture notes, the slides are very brief explanation. I'm not sure if I'm the only person in this class, but like,
Yeah, but
I'd like to
if you don't understand,
know.
you can ask questions during the live session or send me email regarding that or rewatch the we recording. Um, yeah, just if you have any points that you don't understand, you feel free to ask.
Thank you. Okay. Thank you.
Okay, let's continue. Uh, so we already know that the AI is everywhere now, and many large company has like invest a lot of resources into developing those models. Like Google has Gemini, and Microsoft has Copilot, and there are also like OpenAI's ChatGPTs and Anthropic's Cloud and some other Chinese models like Kimi and other stuff. So there are many AI models available now, and all of these models must be built based on this deep learning and neural network structures. And the difference would be they are using different computation units, and they're using some special structures to organize those units, and they have their own training tricks for that. And yeah, so to get into this field, we better learn the basic building unit for this deep learning neural networks. So just quickly jump over that. And okay, so neural networks, it can be defined as a model of reasoning based on the human brain. So the neural network we're going to look at is kind of a mimic of how human brain works. So the human brain consists of a densely interconnected set of nerve cells or basic information processing units called neurons. But the neural network we are going to build will be not we are going to build. It's the neural network structure here we talk about would be a much simplified version. It's just borrowing some core concept from the human brains. So artificial neural networks will consist of a number of very simple processors. It is also called neuron, which is analogous to the biological neurons in the brain. So we can see that on the left-hand side, that is how the human brain neuron, and on the right-hand side is our artificial neural networks neuron. They look like presenting similar structures, but the artificial neural networks neuron is a much simplified version. So we have seen some like very familiar terms here, like Wi multiply Xi plus B is kind of a linear combination between the W vector and the input X vector, and B would be the bias, just like the linear regression, and it it will need an activation function applied after this linear combination. We will look at that later, and then the output will be passed into the next layers of neurons. That is how the artificial neural networks is mimicking the human brain structures. And there are a few variants for the activation function of neurons. So we will look at this in more details later. So here we have a few selections to choose from. So we have sigmoid function, and which can comprise or mapping the value range into the range of 0 and 1. 0 and 1. And we have tangent h function that will map the entire value range into the range between -1 and +1. And we have a ReLU function that will make all the negative values to be 0 and leave the positive value as it. So we will see different situations that to use different activation functions later. So here is just give you a first impression about what activation functions will look like for a neuron. And here is the structure, general representation or illustration of the neural network's structure. So we will have input vector from this would be the input vector. We have seen that we normally we need to prepare the feature vector for each data samples and feed this feature vector into the model. And here, x1 to xn is just representing these feature vectors. They're representing the entry of the feature vector, and each is representing independent feature values. And now we get into the actual neural networks structures. So first, it comes to the input layer. So in input layer, we have neurons. The number of this input layer's neurons will be equals to the number of entries in the feature vectors. So we use one neuron to store the value of one feature. And then we use some edges to connect this input layer to the next layer. So if it is not output layer, it will be called the hidden layer. So all the layers in between or between input layer and output layer will be all called hidden layers. So we use edge to connect each neuron between the two layers. So we can see that the first neuron is connected to all the neurons in the hidden layer, and each neuron in the hidden layer is also connected to all the neurons in previous input layers. So we use edge to connect them. And the values will be processed following some equations inside the neurons, and then the generated output will be passed to the neurons in the next layers. We'll see that later. So the output layer will be also a series of neurons, and each neuron is holding one scalar values. So if we organize this output scalar values in the column vector, we will get the prediction or predicted output from the neural networks model. So this y1 to yl is just the prediction output from the model. So it is you can for now you can just treat it as the, let's say, prediction score or classification score as the output. So here is another representation style for the neural network structures. So the difference is it has more hidden layers. So this is more complex than the previous one. So previous one it only has one hidden layer, but this bottom model has 3 hidden layers. So that means it will have more parameters to tune, and it is more complex and can capture more complex pattern or complicated relationship between the input and the output. Okay, let's look at each the computations between how the values are passed from previous layer to the neuron in next layers. So we have seen this organization of neurons edge in this slice. So that one is just like 90 degrees rotation of this structure representation. So here, this xn1 to xnd would be just the neurons of input layer. So as I said, each neuron is holding one feature value. So in this case, n is the sample index. So it is the nth data point. And this 1, 2, and D index will be the feature index. So in this case, we can see that there will be D features in the input or in the feature vector. So to how these values are passed to the neurons in next layer. So this yn neuron would be the neuron in next layer. So these values are passed to the neurons through this edge, and there are weights on its edges. And it is using the linear combination between the x vector, that is the input or feature vector, with the weight vector. So we can organize this weight on the edges as a weight vector. So they are doing the multiplication and sum them up. So basically what it is doing is xn1 multiply the w1 and xn2 multiplies the w2 and xnd multiply wd. And then we already got the multiplication result, and then we sum all this multiplication result together, and that will be the value passed to the neuron, that is yn. And then recall that we need to apply activation function to the neuron. So we need to apply activation function on this yn after this linear combination between x and w. So we need to apply activation function f on this summation result. So we can use the sigmoid tangent h ReLU function for different purpose, but now we just know that we need to apply this activation function after this linear combination between the w vector and x vector. So here is just an example. This is just using the sine function or the step function, not step function, this sine function. So for positive values, if given positive values, the sine function will produce like positive 1, and if provide negative values, the sine function would provide negative 1. So then after activation function, the value would be the output of this yn neuron. And then this output will be passed to the neuron in next layer. And there will be another weight on this edge, and we will do this weighted combination again and apply another activation function in the next neuron. So let's look at another more complicated example about this process. So if this is just the representation of softmax classifier, if we go back, let me see. If we go back, we can see that for softmax function, so it is multiplying a weight matrix to the input vector, and this is for multiple score, right? If we only have one score, so this is for multiple scores here, multiple scores. But if we only expect one score, then we only need one row of this matrix, right? So there won't be so many rows in this weight matrix. There will be only one row. So we use one row of weight parameters to multiply the column vector, and then the result would be just a single value. So we have seen that these neural networks is just a representation of the software class softmax softmax classifier. So if we will see that if we are expecting more classification score or more output as in the softmax classifier, we can add more neurons in the next layer, and we can see the neural network structure can do all the tasks that the softmax classifier can do, and it can achieve even more complicated task than the softmax classifier. So let's look at this structure. So if neural networks consist of an input layer and an output layer and have one or more hidden layers, then these neural networks will be called the MLP, multi-layer perceptron. So here we have seen the calculation about how the values are passing from the input layer or input vector into the one neuron in next layer, and we repeat the same process for all the neurons in the next hidden layer. So we kind of repeat this linear combination between the weight and x vector and apply the activation functions. So we repeat this computation for all the neurons in next layers, and we can organize them in the matrix form, and that will be similar to the that will be similar to this format, and we'll see that here. So let's just follow this procedure from the beginning. So if we have an input layer or have an input feature vector of 3 feature values, then to calculate the output of HN1 neuron, so we need to do the linear combination between the weight vector W1, W11, so all the red edges, the weight on all the edges, and with the feature vector xn1 to xn3, and then apply the activation function. And to get the output value of HN2, so we need to do the linear combination between W12, that's the weight on this blue edge, W22, that is this edge, and W32 to multiply with xn1, xn2, and xn3. So this will give us a single scalar value, and that will be the result of the linear combination between the weight vector and the input vector. And this value need to be provided to an activation function to get the HN2 result or to get the output of this neuron. So we need to apply the activation function to that. So let's say we apply an activation function f to the result. So here it is using activation function g. So that is just different notation for that.
Excuse me, Doctor.
Yeah.
Do we have to take into account a bias as well?
Not really. Most of the time, you don't need to do that because, like if you are doing the programming, there's an option to include the bias. I think by default, I can't remember by default if it is using or not. But normally, the neural networks is complex enough to work without the bias. But you can try different options for that.
Another question, what determines the K value here, K equals 2? Why did you choose K equals 2 here?
This 2 is corresponding to how many neurons in this first hidden layer. So if there are more neurons, let's say if there are a neuron here and connecting to all the input neurons, so now the K will be equal to 3. It depends on the structure of the neural networks. And I will talk about that later. How to increase the complexity of when I talk about how to increase the complexity of the neural networks, because just like the conventional model, the more complicated model can capture more complex patterns and relationships, but it will require more parameters to tune. That is the trade-off. So we need to find the appropriate level of complexity, but mostly we do it through trial and error and based on our experience. So there's no sum of rules saying like K the hidden layers neurons number is following whatever rules will be the best. There's no such kind of rules to say that. So that's why you see like many researchers are exploring different structure and the number of layers at the very beginning stage of this field. And later on, there are some model structures that shown best performance, showing some outstanding performance, just widely accepted by the field without many mathematic proof. So we just accept those widely used structures. So just in summary, we don't have guidance to say like what number would be optimal for each layer. Okay.
Doctor, another question, if I may. What is like, the exact role of activation function? Is it like to normalize the output of each?
I will talk about the activation function later in next slides. So let me finish this one first. So we have after we have done the calculation between the input layers and the first hidden layers. Now those values need to pass to the output layers. So the value after linear combination and activation function will be just noted as HN1 for first neuron and HN2 for the second neuron. And we can see similar structure here between the hidden layer and the output layer, right? We see these two neurons are connected to the output layer neurons using this edge connected. So we are following the same calculations. So we need to do the linear combination between the v vector and the h vector. So we are multiplying the v1 with hn1 and v2 with hn2, and we sum these two multiplication together. So that will be this term. And then this value is passed to this neuron, and this neuron will be applying another application activation function to the result. And this yn will be the output of this model. So if we are, let's say, if this is if we are using these neural networks to do the house price prediction, and xn1 may be the size of the house, and xn2 may be the number of bedroom, xn3 may be the number of car spaces. So the output here will be just the predicted price from the model. So we are following this computation to process all the input value to the output value. Okay, is there any questions regarding this flow of computation in the neural networks structure?
How do we decide to how many layers we are choosing?
Just like how many there is no rule of thumb to say what is the output number of layers. But what you need to know is the more neurons you have for each layer, the more complex the model will be. The more hidden layers you have, the more complex the model will be. So if you can try with, you may first try a few neurons and just some shallow neural networks, let's say one hidden layers or two hidden layers on your data set. And you may see if you observe some underfitting sign and say, let's say the training and the when you observe the score of the error curve of the training process, if you observe some signature of underfitting, so you may then decide to increase the complexity of the model by either increasing the number of neurons in certain layers, or you can increase the number of hidden layers in your model.
Okay, based on the experience.
Yes, based on the experience and the data, and yeah, but you know how to increase the complexity and how to decrease the complexity.
Yep, got. Thank you.
One question here, please.
Yeah.
So when we are doing the programming in using the neural network libraries or something like that, will I be having an option to declare a variable like a is equal to new MLP, something like that?
No,
being
it's
able
not
to
like the
do
conventional
neural.
model. Let's say you get there's a model named MLP. You need to explicitly specify how many neurons in this layer, how many neurons in next layer, and you manually connect, I would say, connect them in order, and then this connection would be used as a model.
Mhm.
We will see that in the lab.
Thank you.
Okay, if there are no questions regarding this computation, let's move on to the activation function. So as you said, choosing the right activation function is critical and is important. And we have four kind of four mainly used activation functions. Let's say first is sigmoid function, and first, well, we need to get familiar with their characteristic. So for sigmoid function, it will map or comprise the value range into 0 and 1. And for tangent h, it will comprise the value range between -1 and +1. And the ReLU will convert all the negative value as 0 and keep all the positive value as it. And there is another variant called leaky ReLU that is used to fix the dead neuron problems of ReLU, because when we calculate later on, when we calculate the gradient of the loss function, we can see that if the ReLU, if we use ReLU function and if the output of the ReLU function is trapped into let's say if the input of the ReLU function is trapped at some negative values, we can see that the gradient is always 0, right? It is flat in this negative range. And because of that, the gradient on this ReLU function will not provide some meaningful information about how to tune the parameters to change the output of the neuron. So in that case, that means if the neuron is deactivated, let's say if the neuron with ReLU function is holding 0, this value is never changed again. So if the neuron is dead, it cannot come back. It will always be deactive. So to fix that problem, researchers just proposed to use the leaky ReLU. So it will just introduce a minor gradient in this negative range to fix that problem. But ReLU is always preferred as the start. So let's talk about how to choose the activation function. So we choose this activation function based on their characteristic and the location we need to use the activation function. So the first thing we need to consider is where we use the activation function. So there are two places that need the activation function. So the one place is at the output layer, and another place is in hidden layers neurons. So for output layer, we do care about the format or value range of the output values. So imagine that we are doing some regression task. We are predicting the house price, and the price cannot be negative, and we don't want negative values. Then it will be appropriate to use the ReLU function, right? It will just set all the negative values as 0 and leave all the positive predicted price as it. And what if we are expecting a probability? If, let's say, we are doing a binary classification task, and we are expecting the output layer is providing a probability instead of some classification score. So in that case, we may use the sigmoid as the output layer, right? So we want to map the predicted score into this 0 to 1 value range so that the output value can be interpreted as a probability. And in some other cases, we may need the prediction value to be in the range -1 to +1, but that is very rare. I can't think of a situation that we use the tangent H function in the output layer. So that would be about the choice of activation function in output layer. And another choice here for hidden layer activation function is there is some guidance. So based on the experience, ReLU function would be the first one you want to try. And if you meet or observe there's dead neuron problems, if you are monitoring the training process and watching the training error curve, and if you observe such kind of sign about dead neurons, you may want to replace it with some variants of the ReLU, let's say leaky ReLU. And I would say ReLU would be the first one you want to try. So it will provide, it will make the model training to converge quicker than the other two options. But you can still use the sigmoid and tangent H. And the situation is you may want to use this tool when the network structure is shallow. I mean, you have small number of hidden layers. If you have very deep neural networks, like hundreds of layers, you better avoid using that because this tool will cause the gradient vanishing problems. And tangent H is better, but they are still causing the vanishing gradient problem. And another thing is if you are very experienced with this model training process or build your specific model and you have special requirements, you know exactly just like the output neuron, you know that for specific layer, you are expecting the output of the neuron in this layer must be in certain range, like between 0 or 1 or between -1 to +1. You can choose the tangent H or sigmoid accordingly. But the rule of thumb is you'd better start with ReLU. It is recommended. Okay.
So if you use ReLU for hidden layers, are you expected to use ReLU for the output layer, or do you use, can you do mix
You
and
don't
match?
need to use same activation function for all the layers. Like I can use ReLU functions in hidden layers, but for output layer, if I am doing binary classification task, I will use the sigmoid function.
And you would use sigmoid function all the way
Yeah,
through?
because no, for output layer only, I will use the sigmoid function, and for the hidden layers, I will use the ReLU.
Right. Thank you.
But same layer will always use the same activation function. You can use different activation functions in different layer, but neurons in same layer must use the same activation function. And for output layers, what we care more is the format of the output we are expecting. So we are choosing activation function based on our expectation to the output format.
All right. Thank you.
Doctor, quick question. It's a curious question. For neuron, not the activation, for calculation, So we are using linear calculations. Have there been any research or tryouts using nonlinear polynomial functions?
Yeah, good question. I think that's related to why we introduced the activation functions. So you may be curious, like why we introduced this activation functions to the neurons. Why can't we just use the linear combination between weight vectors and input features and so on? Or say, as you said, why we
Yeah,
don't use the nonlinear some kind of relationship,
exactly.
like polynomial, what kind of equations to do that? So why we introduce the activation function is to introduce the linearity to the model. So without the activation function, this kind of linear combination between input and the weight vector would become pure linear computations. So the whole neural network structure will become a linear model. With the introduction of the activation function, the model can we introduce the nonlinearity. The model is complex enough to capture very complicated nonlinear characteristic, and the linear combination. This kind of format is very easy to compute the gradient, and it has some mathematic good characteristic for that. So we don't need the complicated form to calculate such. Let's say we don't need that way, the way you said, like you use nonlinear calculations here to introduce the linearity. We use the activation function.
Right. Thank you, Doctor. If I understood correctly, so it's much more calculation efficient.
Yeah, we achieve the nonlinearity through the activation function instead of using the nonlinear calculations here. Yeah.
Yep. Fair enough. Thanks.
Okay. Okay, all good. So we have seen like previously, we are calculating this HN1 and HN2 values separately using weight vector, using different row vector, multiply the input feature vector to get the result, right? So we can combine these two calculations together in a matrix form. So we can write these two weight vector as two independent rows in this weight matrix. So we can form thereby. So in this case, if we are doing the calculation in the previous fashion, we need to do the weight vector of red multiply the feature vector, and we do the weight vector of blue edges with the feature vector, and we need to calculate the weight vector of green edges with the feature vector. But now we can stack this three weight vector into a single matrix. So now each row is representing the edge on of one color. So we can see that if we do the not each row, in this way it is each column, but it is just transpose of the weight. So now W transpose would be W11 to WD1 and W1K WDK, and then it multiplies the weight vector xn1 to x n d. So we can see that to get the value hn1, we just multiply the first row with the feature vector. And to get the value of hn2, we just use the second row. And to get the hnk, we just use the last row to do the multiplication with the feature vector. So instead of doing this vector to vector multiplication separately, we can do the matrix to vector multiplication directly. And the result will be just another vector, that is hn1, hn2, and hnk, right? Here. And we need to apply the activation function on this matrix to vector multiplication to get the h vector. So we need to apply the activation function on that, not on that, on this one, to get the h vector, just like this. So now this h vector can serve as the input vector to this output neuron, right? We can do this linear combination between the weight vector and the input vector again. So we do this matrix multiplication because there is just one neuron here. It is not matrix. It is a row vector here. The V transpose is a vector now. It's a row vector now. So here V is a column vector, and we transpose it. It is a row vector. So row vector multiplies the vector h that is representing all the values, output values in these layers. And we follow in this linear combination, and then we apply the activation function of this output layer. And the yn will be the result of the model. So this is the structure of providing one single output. So this model is providing one single output. So what if? So this structure can be used to do the, let's say, linear regression, like house price prediction, or binary classification, like the spam email detection. And what if we are doing the multi-class classification task? So we can use more neurons in the output layer. So let's say for digit recognition task, we can use 10 neurons in the output layer so that the output of each neuron in the output layer will corresponding to the, let's say, prediction score or the logic corresponding to one class. So that's the only difference between using some model for binary classification or single value regression task and the model used for vector valued regression or multi-class classification task. So the difference is just on the number of the neurons in the output layer. Is that all right? All good? Okay. And here is a typical representation for the neural networks. So we use neurons, we use node to denote one entry of vector x, and a dense layer is parameterized by a matrix W, and one edge would denote one entry or parameter of matrix W. So this will tell us how many parameters we need to tune. So we need to tune all the weight values between input and hidden layers, and we need to tune all the weight in between hidden layers and output layers, right? And each edge is corresponding to one weight parameter. So the number of the edges in this neural networks will be corresponding to how many parameters we're going to tune in this model. So we will see a more detailed example later, but here we know how to represent the neural network structure. And another way to represent the structure is in this way. So we have a column vector representing the we just have a like vertical block representing the column vector of input, and we have a dense layer. This is just representing one hidden layer. So we specify the width equals to 4. That means there are 4 neurons in this layer. And then the output of this layer will form another input vector to the next layer. And this output of the previous layer would be of size 4 by 1. So 4 is corresponding to the 4 neurons, right? So each neuron is holding one output value. So we need to have a vector that can hold all the 4 values. And this vector of 4 by 1 will be passed into the next layer. And in this hidden layer, we have 2 neurons. And then the output will be passed to the output layer. So this will be the output. So this is not the hidden layer. This will be the output layer because these values are not going to be passed to any further layers. So the last layer must be the output layer. So these 2 neurons will be holding 2 outputs as the outcome. So we need a vector to hold these 2 outcomes. So the outcome would be a vector of 2 entries. So it may be a binary classification task, like one value corresponding to one possible class. And it may also be a multi-value regression task or vector value regression task. Okay, let's just recap how to train a softmax classifier. So we define a function that will map input feature. So that will be the total number of pixels in the given image. And we map this feature vector to a vector of 10 classes. So this will be a probability vector. Input is a vector of 785 pixel values. And then we use this weight matrix and vector multiplication form to generate the prediction score, right? And we need to convert this vector of score into a vector of probability. So we apply the softmax function. And how can we solve this model, or how can we train this model? Is we are going to build a loss function using the cross entropy by comparing the y, that is the binary true label vector, that is y, and with the log of the probability vector, and then we take the negative, that's the cross entropy. So with the loss function defined, we can solve it using the certain optimization method. Maybe we can use the gradient descent method to do the optimization and find the optimal values in this W matrix.
Sorry, can you just explain that argmin? What is this?
Argmin means find the argument that minimize this function. And the argument is W. So that means find the value for W that can minimize this function's value.
Okay, thank you.
So it is just a notation. So yeah. Okay, from the linear model to neural networks. So let's see what's the difference. So here is we'll talk about how many trainable parameters, like how many parameters we need to tune. So this is a model, neural networks of two hidden layers. So first we have the input layers. We define two hidden layers, and the last hidden layers will be connected to the output layer. The input layer, obviously, so can you tell me how many neurons in this input layer? So this should be 785 neurons in the input layers because we need one neuron to store one values in the feature vector. So one neuron corresponding to one entry in the input vector. So this input vector is input vector has 785 entries. So we need the same number of neurons for the input feature. And for the first hidden layer, we have D1 number of neurons, and we do the linear combination between the weight matrix and the input vector, and this is the ReLU activation function, right? So we apply this activation function after the linear combination between weight and input. And this X1 will be the output of the hidden layer 1. And the output is provided as the input to the hidden layer 2 and need to go through the linear combination with another weight matrix. This is the weight matrix between hidden layer 1 and hidden layer 2. And this is the result of linear combination. And we still need to apply the activation function, this is ReLU function, to this linear combination result to get the output of hidden layer 2. And the hidden layer 2 will be connected to the output layer. And this output layer has 10 neurons corresponding to 10 possible class. So this the previous layer, the hidden layer 2's output will go through the linear combination to get the linear combination result. And this Z3 will be the, let's say, prediction score or the logits, the vector of scores. And we need to apply softmax function on this vector of scores to convert this Z3 to X3. So this X3 will now become the probability vector, right? So with this data structure, neural network structure defined, we can know that all the parameters we need to tune are in W0, W1, and W2. And they are representing all the edges between any two adjacent layer, right? So the number of entries in this W0 will be D1 multiply 785, right? This is the number of edges between input layer and hidden layer 1, right? We have 785 neurons, and we have D1 number of neurons in hidden layer 1. So to fully connect these two layers, we need this number of edges to fully connect these two layers. Similarly, this is the number of parameters in between hidden layer 1 and hidden layer 2, and we need 10 multiply D2 numbers of parameters to tune between hidden layer 2 and output layer. So these three, the sum of these three will be the total number of trainable parameters. This is total number of parameters we need to tune. So this will give us an insight of how complex or how large the model will be. So the more number of parameters to tune, obviously, it will cost more time to optimize and to find the optimal values. And here we use sigmoid softmax functions because for multi-class classification, we need to convert the prediction score to the probability vector so that we can compare with the true label binary vector to form the loss function. So we need to use the softmax function. And for the layers, for the hidden layers 1 and hidden layer 2, we use the ReLU function because that is the first choice we want to try. And for output layer, as I said, if we are working on the binary classification problem, we can use sigmoid or tangent H function, but sigmoid function is preferred. And for regression task, we don't need activation function at the output layer. If we know for sure that the output must be all positive, we can use the ReLU function at the output layer. If there is no such restriction, we don't need to add any activation function at the output layer for regression task, because regression task is just predicting continuous value. So if there's no restriction, so we don't need any activation function. Is it all right for now? All good? Okay. So let's so how to find the optimal value for this weight matrix? So we need to use the gradient descent method to minimize the loss functions. So here we talk about the stochastic gradient descent method. So for this method, it will randomly pick one sample from all the data set. So just one sample. And then it calculates the gradient of loss function with respect the partial derivative of loss function with respect to each parameter variables, and then update the weight values towards the negative of gradient directions. This alpha, as we said before in the conventional method, this alpha is the learning rate or step size, and this Gj would be the gradient or the partial derivative of loss function with respect to the weight matrix. And the result would be the tuned or new weight values in this iteration. And we do this calculation of gradient and update of the weight values iteratively. So we do this, repeat this process iteration by iterations until we find the optimal value of W0 matrix. And we do the same process for W1 and W2. So the difference is we are using different gradient So we are calculating the partial derivative of loss function with respect to either W1 or W2. And we update the W1 matrix following the negative direction of gradient, and update the W2 matrix also following the negative direction of gradient. So we repeat the process on W1 and W2 updates. So this is how we calculate how we find the optimal value for all the trainable parameters. The core or the important thing is for stochastic gradient descent method, we use only one sample for the gradient value. So later on we will see other variant for the gradient descent method.
So one sample for one backpropagation cycle.
Sorry?
In stochastic, I don't know if I'm pronouncing it correctly. So in that algorithm, we pick one sample for one backpropagation iteration.
Yes, for stochastic gradient descent, we just use one sample. So we have n data point. We have n input samples, right? So we use one sample, and we use it to calculate the gradient. We update the value. We have to update all the weight values, and that's done for one sample. And then we repeat the whole process. Let's say we choose another sample and repeat the update process. And we then choose the next sample to do this update process. So this is how stochastic gradient descent is doing. So you may wondering, so we can choose multiple samples to do this update process, and we can also use all the data samples to calculate the loss and gradients. So those are two variants. We will talk about that later. So
quick clarification on that one. So when we pick one sample and we do the backpropagation, we update the gradients. We calculate the gradients and we update the weight. And do we do a feed forward and pick another one, or just without a forward, we pick another random sample and do the same?
Yeah, we should. I will talk about that in next slides.
Oh, thank you.
Is it one sample, one layer, or just one sample, the whole layers?
One sample, the whole layers. One sample we use one sample and we update all the layers. So let me finish the forward propagation and forward pass and back propagation, and you may have like better understanding.
Okay, thank you.
So we first is randomly pick one sample. So we have the feature vector, and we have the corresponding expected output, right? No matter if it is a classification or regression task. So we have input feature vector, and we have the expected output. And we run a forward pass. So that means we have all these input layers neurons set for this sample, for this input sample, right? So we know the input value for this input layers. We have values for all these neurons, and these values will be passed to the hidden layer 1. So we are doing the linear combination and activation function. So to calculate the output of the hidden layer 1, and the output will be passed to the hidden layer 2 also through the linear combination and activation function, and so on. So all this process will be following the direction from input layer to output layer. So that's why it's called forward pass. So after the forward pass, we got all the layers output, right? For the edges, we have some, let's say, randomly initialized weight on all the edges. So we can do all this forward direction calculations. And at the output layer, we will get a prediction. So we can expect that this output is wrong, is very wrong, right? Because all this value of edges will is initialized randomly and without any training. So this prediction must be very wrong from the label or from our expectations. So, but anyway, we compare the the current stage model prediction with our expected true values, and we build a loss function based on such comparison. Let's say for regression task, we may use the mean square error. Like for multi-class classification, we are using cross entropy. But no matter what task we have, we can have a loss function. And then after we got the loss function, we are going to run a backward path. So with the loss function defined, we want to know how to tune each parameter or how to tune the weight on each edge would affect the value of the loss function. So we want to know, let's say for specific, let's say for this weight value W11, I want to know if I'm going to tune the value to be larger or smaller. So if the gradient says if the gradient is positive, that means the larger the W value, the larger the loss value. But our purpose is to minimize the loss value, right? So that will suggest me to tune the value of W11 down. So we want to use a smaller value in the next iteration so that the loss function can become smaller and smaller. So our purpose for backward propagation is we want to calculate the gradient of loss function with respect to all these weight values. And we need to calculate this gradient in following the reverse direction. We need to calculate the gradient layer by layer in this backward direction. So that's why it's called back propagation. So we want to calculate the loss function, the partial derivative of loss function with respect to each weight parameters. But using the chain rules, we must following the backward direction. We need to calculate this derivative from the output layer and then calculate the derivative on the hidden layer 3 and then the gradient on hidden layer 2. So we need to follow in this direction. But the purpose is we want to know how to tune each weight so that we can get a lower loss value. And this would be a more detailed computation or example of the backpropagation. It will require some knowledge of the derivative and partial derivative. You're not required to remember these derivatives, but you need to know like what information we need in this backpropagation process.
Doctor, after backpropagation, do you use the refined values and go forward again? No?
We need to, it is a kind of repeated process. So in one iteration, we following the forward path
Yes.
to get the loss value, right? And then we calculate the gradient in the backward propagation. And now all the weight value is updated. We have new weight values. Then we need to know what then if we have the new weight values, then we must have a new loss values. So we need to do the forward pass again to calculate the updated loss values. And then with the new loss values, we need to calculate the updated gradient for all the layers and weights. So it is kind of iterative process. We do the forward pass to find the new loss value, and based on the new loss value, we calculate the new gradient.
You do it for the same data set, no?
We do it for the same sample.
Okay, yeah.
Yeah.
And when do you stop the loop?
When you find the optimal. When you find the optimal, like say if the loss function is not changed or the difference between two iteration is under certain tolerance number, or you may set a maximum iteration number. So there are let's say if you are using the framework, the TensorFlow or PyTorch, there are some default values set for the optimizer. So, but the underlying criteria is if the loss function is stable and if the iteration is reaching the maximum number. Okay?
Okay.
Okay. So let's just look at this example. So first, we choose a random sample from the data set, and then we need to use the forward pass to calculate the loss, right? We need to follow the forward pass. So we take xj, that is the feature vector, and supply it to the input layer, and we use the neurons to save all the entry values. And then we follow in the forward pass direction to calculate the output of each layers. We need to calculate the linear combination result of layer 1 and what's the value after activation function. And the output is provided to the next layer. So we need to calculate the linear combination result, the result after activation, the linear combination result of next layer, what's the value after activation, and this three is the output of last layer. So it is the activation linear combination result. And that is done for forward pass. And for backward propagation, we have already got the fx, right? So fx is equals to this three. So this is the output of the model. And we can see that the value of f is depending on the x0, that is the input we provide to the model. And we then calculate the gradient. We first calculate the loss, right? We already got the prediction from the model, and we compare it with the true label, and we calculate the square difference because we want to maintain the loss value as a positive value. So we use square, and we divide it by 2 because that is convenient after we calculate the derivative. So we first can calculate the partial derivative of loss function with respect to this three. And this is the partial derivative result. So you can just, so this fxj is equivalent to this three. So if you just replace it with this three and calculate and treat this three as a variable and calculate the derivative, you will get the same result as this one. Since this three is the output of forward pass, so this value is known. So this three is known. Yj is the true label that is also known. So we know the value of this partial derivative. So this partial derivative value is known. And then we keep calculating the gradient in previous layers. So we want to calculate the the partial derivative L loss function with respect to Z2. And using the chain rule, it is equivalent to calculate the partial derivative of L with respect to Z3, multiply the partial derivative of Z3 with respect to Z2, and the detailed derivation you can check here. It will require some knowledge about derivative calculations. And based on this, and we can also calculate the partial derivative L with respect to weight matrix W2. And again, using the chain rule, it is equivalent to calculating the partial derivative of L with respect to Z3, multiply the partial derivative of Z3 with respect to W2. And this partial derivative is known in previous step, right? And this partial derivative is can be calculated using this equation. So Z3 with respect to W2 is just X2, right? So this one is known, this one is just known. So we got the value for this partial derivative. We got the gradient for W2 matrix. And now we know how to update the value of W2 matrix. And then we do the update. Until now, we have done the process back propagation process to the hidden layer 2. And now we should keep doing this backward propagation. So we calculate the partial derivative with respect to Z1 and also partial derivative with respect to W1 weight matrix. And I won't go through this again. So you just know we can calculate that in this fashion. And with this partial derivative calculated, we know how to update the weight matrix 1 again. So we are following just gradient descent, the negative of the gradient direction to update the weight values. So we do this backward propagations and gradient values to the forward path until the input layer. So here is just a summary for this back propagations. So for one iteration, we pick one data sample from all the data set, and we use the forward path to calculate the output of each layer, and also the linear combination result, the result after activations for all the layers. And for backward path, we need to calculate some derivatives. We need to calculate some the partial derivatives of loss function with respect to all the output value of layers, and also with respect to the weight matrix. And we need to use this gradient or derivative with respect to weight matrix to update all the weight values. So one iteration, one series of updates, one times of update for each weight parameter. This is for one iteration. And in next iteration, it will pick for stochastic gradient descent, it will pick another sample from the data set and do the forward pass, and then do the forward pass and update. So one iteration, one sample, one time update. Okay? Okay, this is a summary. We have repeated that. I'm not going to repeat it. Okay, let's look at another variant for the statistical gradient descent. So it is called mini batch gradient descent. So instead of using only one sample to do the forward pass, we are using several random samples. We are not going to rely on a single sample to calculate the loss and calculate the gradient. So we want this calculation or update to consider more thoroughly by including more samples in one times of update. So that's the only difference. So we now choose several random samples from the entire dataset. And the same, we run a forward pass and we run a backward pass for that. The difference is the way we calculate the gradient. So now we need to calculate the loss function for each random sample we choose. We need to calculate their individual partial derivative, and then so each partial derivative will give us a direction for update, right? So we need to sum them together to make a final update direction. And we do this all the weight metrics. So we consider all the suggested update direction by each random samples, and we sum them together and calculate it an average. So this will give us an average moving direction for all the weighting parameters. And so in this way, for each update of the weight values, the method is considering the information more thoroughly. So it is considering more information from the dataset instead of relying on single dataset for update. So that's the difference. And you may also wondering, can we use all the data samples to do one-time update? Yes, we can. That is called full gradient descent. But normally we don't do that because it takes a lot of time and it takes a lot of memory. When we do the forward pass and backward propagation, we need to store all this intermediate value in the memory. And you can imagine that if you have a very large data set, let's say you have millions of data points or millions of images to process, and if you include all these images in the memory and also the intermediate result, it will be a huge challenge for the size of your memory and computation power. So it is not feasible for the training of neural networks, and especially for very complicated neural networks. So that's why in practical, we don't use the full gradient descent values. And for stochastic gradient descent method, it is considering only one sample in each iteration. So per iteration cost is low, but you would need lots of iterations to converge. And if you monitor the trajectory of the loss function, the loss value, you may find some like zigzag path using the stochastical gradient descent. The path will be not that smooth. because it is relying on single data samples. So we need to find a trade-off between the statistical gradient descent and the full gradient descent method. So that comes with the mini batch gradient descent. So we don't consider all the data points in each iteration. We just split the entire data set into small batches, and we use small batch to update. We use small batch in each iteration to update the value, so it will achieve a better balance in comparison with the stochastic gradient descent and full gradient descent method. So this is mini batch gradient descent is our preferred choice. Okay. So here is a summary of today's content. So we talk about the network structure. So basically, we need to consider how many layers to build in this network, and how many neurons in each layers, and what kind of activation function we need to choose for each layer, for the hidden layers and for output layers. And how can we determine the total number of trainable parameters in the in specific neural network structures? And what can be the candidate of loss functions? So we use cross entropy for classification tasks, especially for multi-class classification tasks. For binary classification, we can use the sigmoid function, or L1 and L. We use squared L2. We can use the squared L2 as a loss function. And for regression tasks, normally we use L1 or squared L2 norm as the loss function. And to compute the gradient or do the back propagation, so we need to consider to use the mini batch gradient descent method. We need to consider the batch size. So normally, the batch size should be a multiple of 8. So, and it means you may choose a batch size of 8, 16, 32, 64, something like that. And you don't need to worry about to implement this calculation of gradient and loss function by yourself. So those are already built into the deep learning framework. So if you are using TensorFlow or PyTorch, they already support that computations. You don't need to worry about that. And there are many options for the optimization algorithm. You can use the stochastic gradient descent method, or we can add some momentum into the optimization, and we can use the adder gradient method or RMS prop. So there are many options that you can play with. Okay. Okay, that will be all for today. I will leave this video to you to watch in your own time. Okay, so sorry for the delay. There are a lot of contents to deliver in this week. Is there any questions? All good?
Thank you.
Okay, great. Then I will see you all on Friday night.
Thank you.
Thank you so much.
Thank you.
Have a good one.
Thank you, Doctor. Have a good night.
You too.
Have a good night.